So we have seen that how the state of mind actually changes depends on how actually we can uh, draw a diagram considering some state of minds and their transitions with respect to different problem. Now from this point, from this diagram, we can try to realize the formal definition of a finite state machine. Automaton or automata can be represented by these five tuples. So these are the five tuples we have seen when we have solved the previous problem. First is a finite number of states that we represent by capital Q. Then a finite input alphabet represented by sigma. I mean, the finite state machine is going to accept some particular language, and that particular language must have some particular alphabet. So that's why this alphabet is also a very important member of this five tuple. Third is that Q0, which represents initial or starting state. Always remember one thing, Q can be a set. Sigma is again a set of symbols, but Q0 is not a set. Q0 is only a single state which belongs to capital Q. So if we have a finite state machine may contain n number of states. The problem is very easy in previous case. That's why we had only two state of mind. But if I just extend the previous problem a little bit, for example, I say that okay, I want to create a finite state machine that will accept a language where the strings of the language will be accepted only if the string contain even number of zeros and also even number of ones. So here, if I extend this problem in this way, your state of mind will entirely change, because in the new problem we are not considering only number of zeros, we are also considering number of ones. I mean whether they are even or not. So at the very beginning, I mean of the before you about to start read the characters of the string, your your state of mind is not about only number of zeros you have seen. I mean even number of zeros you have seen. You have not seen any one also. That is even number of one. So even number of zeros and even number of one is possible. I mean up to some amount of transition, it may happen that you have seen n number of zeros and m number of one. And this n and m can be anything. Anything in the sense that both n and m can be even, both n and m can be odd, n can be even, m can be odd, n can be odd and m can be even. So if we just extend the previous problem to say that we want to accept only even number of zeros and even number of ones, I mean the strings containing even number of zeros as well as even number of ones, then your state of mind will, at least the state of mind that you require should be 4. One state of mind will say even number of zeros, even number of one. One state of mind will say odd number of zeros, odd number of one. One state of mind will say even number of zero, odd number of one, and one state of mind say odd number of zeros and even number of one. Various combinations. So your state of mind from 2 it become 4. But among these 4 state of mind, one of them is the initial state of mind. Initial state of mind means that when you are about to start reading the characters, what is the state of mind at that point? If I say you are about to start, that means you have not visited any zeros, even you have not visited any 1. So number of zeros you have seen is 0, even number of 1 you have seen is 0. So both are even. That means among these 4 state of mind, your initial state of mind is even number of 0 and even number of 1. So this is what we will see what can be the solution for this one, but what actually my intention is to say is that this Q0 that is represented over here is not a set of initial states, it's a single state. It's not a set. But a final state can be anything. There can be a number of states which can be final. So that is represented by capital F. It's written that a set of final or accepting states which is in the subset of Q. Obviously, everything is a subset of Q. F, Q0, all are subset of capital Q. But a very important difference between this Q0 and F is that Q0 cannot be a set. It's a single state. But F can be a set. That means I can have, depends on my requirement, we will see later that it's possible that we're having 2 different final states. And obviously, a function is required for jumping from one state to another state. What I mean to say is that if you take this diagram and if you are in this particular state and if you see 1, you will remain in this state. How you can express it? We have to express by some function. That function we call transition function, which defines the transition between 2 states for a particular input. Now this 2 state can be same state and 2 state can be different. For example, transition from even number of 0 state to the even number of 0 state, because of this 1 should be represented by some transition function, and that transition function we represent by delta. Now see, if we have say n number of states, and if an alphabet contain p number of symbols, that means there is a possibility to change your state of mind from one state to one of the n states of the system because of one of the p symbols. So that means if you are in one of the state belongs to Q, if you are in one of the states belongs to capital Q, and if you find a symbol belongs to this alphabet, you will go to another state which will belongs to this capital Q. Now, how many combination is possible? That is important. How many combination mean how many total number of combination is possible? Total number of combination is possible is capital Q cross sigma. Why it is capital Q cross sigma? Because as I told you that if I say that let's take an example, very simple example, that we have say two states. Just previous example you see. We have two states. And say this is Q1 and this is Q2. Okay. We represent it by Q0, doesn't matter. It can be Q1 also, some symbol. This is your suppose initial state. Now, suppose alphabet is A, B. So, if you are in Q1 and if you symbol, I mean maybe in the string is say A, B, B, A. Suppose. On reading this on reading this A from Q1, you will either go to Q2 or you will remain in Q1. Now, question is that how many transition possible from this Q1? The number of transition that is possible from Q1 is 2. Why? Because one will be for A and another will be for B. Similarly, number of transition possible from Q2 is also 2. One will be for A and one will be for B. So total number of transition as a whole it is possible is 2 into 2. What is this 2? These 2 is number of states. And what is this 2? These 2 is number of symbol. That thing actually expressed over here. This Q means total number of finite set of states. Sigma is representing the input alphabets. And the function maps Q with the sigma to one of the state again. That means that's why arrow to Q. And that is actually written over here. You see, delta is a function represent from this to mapping from this set to this set. So it's defined for any Q in capital Q. Any Q means any set belong to the set of states Q, and S, some symbol, belongs to this alphabet and is equal to some state Q dash. Q dash is again within some Q, capital Q, and it can be Q dash equal to Q. This is very important. What does it mean? It means that we have a self loop. Say for A, suppose. So you are in Q1. If you are in Q1, suppose I am writing a function. If you are in Q1 and if you are find a symbol A, where you will go? You will remain in Q1. So this one can be, in a general way we can represent that if you are in say Q and if you find a symbol S, you can go to P. P is, and both P and Q belongs to capital Q. So the general form of this one is this, or maybe you can say a special form of this one is this, which represents the self loop, and that also we represent in this way, just like what I have written over here. Same thing, same type of representation. Here it is expressed as Q dash. I have expressed as CP. That is the difference. And that's why this transition function can be also defined by a table, and that we call state transition table. This state transition table takes present state, the symbol that it can see, and depends on this what should be the next state. So for example here, I mean the uh, state transition table that is written over here is representing this previous case. So if you consider it is Q0 and it is represented as Q1. So you see, if you are in Q0 and if you get a symbol 0, you will jump to Q1, right? That is represented over here. If you are in Q0, if you got a 0, you will go to Q1. Again, if you are in Q0, you get a 1, you will remain in Q0. And that is represented over here. If you are in Q0, you get a 1, you will be in Q0 again. And similar thing for Q1 also. I hope you can easily understand. Anyway, by mistake I have written this capital Q, but generally we write every state name as small letter. So if we want to write with respect to a transition function, not a transition table, I should say I will write over here, that is del Q0 0 will be equal to Q1, del Q0 1 will be equal to Q0, then del Q1 0 will be equal to Q0, and del Q1 1 will be equal to Q1. So I will have 4 transition function, and that's why you have 4 rows also in the sequence. So this is a way by which we can express the transition of the states, transition between states in a state diagram of a finite state machine. Now we have to realize some very important points regarding this finite state machine. That is, so I mean, let's try to go through each and every point, try to realize what it means. What is written in the first point, that let M is a finite state machine having these 5 tuples Q1, Q, sigma, delta, Q0 and F, be a finite automata, and let W be in the sigma star. What is sigma star? Sigma star means any combination of sigma. Sigma is what? Sigma is specially this is not a universal sigma. This is not a universal sigma. This is a sigma of this particular finite automata. Okay, so W in sigma star mean W basically is a string which is any combination of the symbols of this sigma. A very simple one. Then W is accepted by M. This IFF means if, this means if and only if. Okay. If and only if, what is written? Delta Q0 W equal to P. Mean that on reading the string W, if you are in Q0, that is your initial state, at least with respect to the representation of this machine, Q0 is the initial state. So if you are in initial state, on reading this W, if you reach to a state that is P, such that P is in F, means P is one of the final states. Then you can say that W is accepted by the M. So this is a way by which we actually express how the mathematical definition of accepting a particular type of language by a machine. Okay. So now, for example over here, you can say, let's take this example. So I know that if I write say 1001, is it going to accept by this uh, particular finite state machine? No, because we have kept odd number of zeros as final state. So here 0 is even. So okay, so let's keep it odd. This should be accepted by the machine. So from this is Q0, this is Q1. So I can say that del Q0 10010 is what? Q1. Means on reading this character, this string, if you are in Q0, you will reach to Q1. Now since Q1 belongs to final state, that's why this W, this is our W, right? W is accepted. So this is the way of expressing what language will be accepted. Okay. Similarly, you can also say the similar type of situation. You can say actually we have different way of expressing the same thing. Various books or various source will express the same thing in different form. That different form we are different definition actually we are discussing over here. The next one is saying that let again M be a finite automata. Then the language accepted by the M in the set is defined in this way. You can say that a language W in sigma star and del Q0W is in F. Similar thing, same type, same definition, but writing for expressing in a different way. Again, a different form, I can say that the LM equal to W. That means LM means a language generated by this machine M. Okay. So language generated by this machine M should be W, where W is in sigma star. That is very trivial. Now important is this second point. W is accepted by M. As simple as that. And W will be accepted by M only when this particular situation will arise. Right? When P equal to set of final state. Now this fifth point is going to be very vital. What is said that let L be a language, then L is regular language if and only if there exists a DFA M such that L equal to LM. What does it mean? It means that if a language is accepted by a finite state machine, then that particular language is called regular language. So the grammar is also regular grammar. So if someone asks you to prove that some language is regular, what is the best way to prove it? That you have to design a DFA that accepts the strings of the language. As simple as that. If there is a DFA, then the language is regular. So, naturally question will come that what if the language is not regular. So we will see it very soon. We will see that situation later. But today we will consider only for finite state machine. And the second last point is that let M1 is a finite state machine, M2 is another finite state machine. Okay. Now this M1 and M2 can be equivalent. We can say if and only if the language generated by M1 and the language generated by M2 is same. Like this. If this both set is same, then only I can say that the machine M1 and M2 are equivalent. Similarly, so we will now uh, we will concentrate on a special type of finite automata that we call deterministic finite automata. Now, why it is deterministic? Say because it's written that on seeing a symbol of a string, there is a unique direct path from one state to reach to another state. What I mean? I mean that let's see if you are in Q0 suppose, and if you get a particular symbol, for example, at least from this state diagram, we can say that your alphabet is consist of A, B, and C, right? So on if you are in Q0 on seeing A, you will have a deterministic path to reach one of the states. For example, you are in here. So let's make it much more simple. So suppose that I have a state Q0 over here. I have one state Q1 here, and I have a state Q2 here. I'm taking an arbitrary diagram. Suppose this is your initial state. Okay. If you start, if you get a 0, I mean, we say A, if you get a A, you will reach to this state. If you get a B, you will reach to this state. So this path should be unique. Mean from Q0 on getting a symbol A, it's not possible to have multiple paths for the same symbol. And that's why it is deterministic. And one more thing is also there. One more point, very important point, is that from a particular state, the path, I mean, let's write it over here, which is not written, from a particular state on reading a symbol, actually on reading a symbol, it's not wrong, it's not true, sorry. From a particular state there must have unique path for a particular state, there must have a unique path to reach one of the states for every symbol belongs to sigma. What I mean? I mean is that if I assume that sigma is ABC, then you must have a defined definition that if you are in Q0 on seeing symbol C, what you will do. You cannot end up with A and B only. Maybe for, on seeing C, you will remain in this state. It may happen, but you have to express it. And that is what I've written. That from a particular state, there must have a unique path to reach to one of the states for every symbol belongs to alphabet. You cannot ignore even a single symbol. And you see, it's same situation is represented in this diagram also. From Q0, I have a path for A, path for B, path for C. Similarly, for Q1, I have a path for A, path for B, path for C. And similar thing for Q2. And Q2 is final state. How we can understand? Because of this double bordered circle. And Q0 is the initial state because of this arrow. So, this is a example deterministic finite automata, or in short DFA, which is also a part of finite automata. So we will see, now we will see that what are the different type of deterministic finite automata that is possible as an example.